I thought we'd just start off with some background information on what the problem is that we're currently facing in the space industry. It's a multifaceted problem in that we know that space is expensive, but there is a lot of confusion about how expensive it actually is, or will become in the near future. There are also concerns about the environmental impact of chemical rockets. There is very little consensus about whether there is any viable alternative to using chemical rockets, even though, thanks to a startup called Spin Launch, we have begun to see some real money being invested into alternative technologies. The numbers we're talking about are staggering, in the hundreds of billions to hundreds of trillions dollar range, depending on who you ask. Some of the goals that people are kicking around in space, in the space industry, involve establishing a self-sustaining city on Mars or moving all heavy industry out into space so that we can zone Earth as entirely residential and commercial real estate. Now, while we're going to talk about some of these numbers and how space launch infrastructure can help bring costs down, I'd like to keep in mind that the goal of this presentation is much more modest. What I'd like you to come away with is a belief in a simple idea. And that idea is that right now we need to start developing the institutional infrastructure that will one day develop the hard infrastructure that we will need for humanity to be able to expand out into the solar system. Humanity has some great ambitions in space. It will be incredibly expensive and potentially harmful to the environment if we try to achieve these dreams by using chemical rockets. Space infrastructure could save us trillions of dollars. But if we want space infrastructure, we'll need research infrastructure that is dedicated to developing space infrastructure first. To develop space infrastructure or develop the research infrastructure, lots of scientists in a variety of different fields will need to be convinced that cracking the problem of hard space infrastructure is challenging but has enormous value. And that is the purpose of today's presentation. Now, to begin with, I want to expose you to some direct sources of information about the high cost of our space ambitions. Then I'm going to talk a little bit about a reference mission. And then we're going to select a chemical rocket-based system and use it to evaluate the mission cost. Then we're going to go and define some requirements for selecting a suitable space infrastructure. And we'll use those requirements to actually select an infrastructure. And then once we've selected that infrastructure, we'll do a little bit of a deep dive on it and then evaluate the mission cost with the space infrastructure. And at the end of the presentation, we'll compare those results. NASA has published and periodically does publish roadmaps of what they want to achieve. This is an example of what they're doing. They've got 3 different categories or technical challenges they're tackling. And if you look at the first item on each of these challenges, it's the same. It says dramatically reduce the total cost and increase the reliability and safety of access to space. Recently at the House hearings on Artemis, we heard a little bit about the cost and the mission objectives for our plans to go to Mars.
Our ultimate goal is getting 2 people to Mars on the surface for 30 days. Everything we do should be driven by that on the moon.
Critical to NASA's efforts to land humans on the moon as a precursor to a crewed Mars mission. We estimate NASA will spend $53 billion on Artemis from 2021 to 2025.
The Inspector General's report on NASA's management of the Artemis program states that $25 billion should be added to the Artemis plan's projected cost.
There's a whole series of capabilities that are being developed as we speak now that we total up to be approximately $25 billion that are not reflected in NASA's current Artemis cost estimates.
In a hearing of the House Science, Space, and Technology Committee, Congressman Bill Foster asked the director of NASA whether they considered working on space infrastructure.
You're talking about Essentially a program based on chemical rockets that would be completely understandable to Wernher von Braun, everything you're proposing. And there have been for, decades, conceptual designs for ways to get stuff into low Earth orbit for much less. For example, these are things like electromagnetic launch systems. And is that something that bothers you, or have you considered moving the needle on that so that actually we have a chance 50 or 100 years from now with having space be affordable to people, which I think is pretty clearly not going to happen if we just keep using chemical rockets again and again.
So the QR code in the bottom right will give you a link to the full video where you can see the NASA director's response and some more discussion on this topic. More economic data. Bank of America thinks we're going to spend $1.4 trillion within a decade. Robert Zubrin says we might have the technology to put boots on the ground on Mars, but we're going to have to develop some new systems if we want to colonize Mars. So we created a reference mission which involved putting 500,000 metric tons on the moon and 1 million metric tons on Mars over a 50-year time frame. To put that in perspective, this is just 2.26 semi-trucks per day. So if you can imagine building 2 cities, but you're only allowed to use 2.26 semi-trucks per day to do it, that's pretty challenging. We want to try to figure out the cost of doing this with chemical rockets. So the way we're going to do this is we're going to look at ISS resupply contracts, adjust for inflation, try to figure out what their payload manifests were, and combine the data to generate a Falcon 9 cost per kilogram. And then we're going to apply technology change factors and weights to try to convert that data into data for Starship, which is a system that's more optimized for the task of going, or the mission of going to Mars and the moon. These are commercial resupply contracts that are downloaded from usaspending.gov for SpaceX ISS resupply. This is the data from the payload manifest for those same journeys to the ISS. And we can combine these two curves to get a sense of the amount of money being spent versus the payload being delivered to the ISS. And we can fit a curve, this data, and from that curve, the slope of that curve, or the inverse slope of that curve, represents the actual cost per kilogram. And this is what this graph is showing us. So the cost per kilogram initially was as high as $425,000 per kilogram. And over the years, it's been dropping, and it seems to be leveling out at around $68,000 per kilogram. Interestingly, this aligns well with that 2018 report from the Office of the Inspector General. They also predicted that it would end up around $71,000 per kilogram. Now we need to convert this number for Falcon 9 making trips to the ISS to Starship, because the Starship program is a new program, more optimized for Mars. So to do that, we created a table of differences between Falcon 9 and Starship. These are all the differences on the left, and created weighting factors, like how much the technology difference should increase or decrease the cost, and the weighting of that factor to the overall system. And the finding from this exercise was that there's almost no difference between Starship and Falcon 9 in terms of the effective cost per kilogram. There's no technical reason why Starship should be significantly cheaper than Falcon 9. So the end result now is that we have a cost per kilogram for Starship. We do need to do a refilling factor, because these numbers are all for getting to low Earth orbit. In order to get to Mars, we need to send up 5 additional Starships to refill the Starship that's going to Mars. So the 5 Starships for refilling plus the one that's going to Mars means we need a refilling factor of 6. So the cost of the mission basically ends up being the mass we deliver times the refilling factor times the cost per kilogram. And if you do that math, it works out to $607 trillion US to achieve our reference mission for Mars and the Moon. There's a number of additional considerations, but I'm going to skip over those for now. So we got our estimated cost for the mission using chemical rockets. Now we want to define some requirements for selecting a suitable space infrastructure. And then based on that, we'll select the infrastructure and do a deep dive on the selection. The full paper goes into a lot more detail about how we did this, but essentially we created some basic requirements and then we use them to filter all the different proposals out there for non-rocket type technologies. Only 3 technologies made it through. All of them were stratospheric electromagnetic launchers that were supported by either space fountains, a Lofstrom loop, or a tethered ring. This slide talks a little bit about some work that NASA's and the U.S. Air Force Office of Scientific Research has done on electromagnetic launch. Both have concluded it would be feasible. Now, the space fountain is this idea on the left. The Lofstrom loop is this structure that's up in the stratosphere, and a tethered ring is a structure that goes completely around the Pacific Ocean. We need to filter between those 3 structures. The way we did that was by considering how difficult it would be to adapt existing technologies such as magnetic bearings and maglev train technologies to each of these architectures. We created a list of criteria here that would make it easier or harder for the technology to be implemented. We created a table where we compared the 3 systems and found that the tethered ring was the system that had the lowest technology adaptation degree of difficulty of the 3 types of systems. So now we've gone through our requirements and selected an infrastructure. Let's do a little bit of a deep dive on the tethered ring itself. So tethered ring is built on the Earth and then raised into the stratosphere by the action of tensioning its tethers. Inside the tethered ring, there's essentially a pipeline that goes around the Pacific Ocean. Now, inside that pipeline, there's an electromagnetic levitation system which supports another ring that floats on the magnetic system. That creates inertial forces which are represented by these red arrows. Tethers are then attached between the ring and the surface of the Earth, and by tensioning the tethers, we create a tensile force, which is shown by these blue arrows. The combined inertial force and tensile force add together to offset the force of gravity. And this is how the ring can be essentially lifted up or pulled away from the surface of the Earth and raised up into the stratosphere. Now, a tethered ring is useful for more than just space launch. It's a multi-use structure. So one of the business models that is supported by a tethered ring is terrestrial transit. In other words, making carbon neutral international travel possible. The way this would work is we would have an evacuated tube transit system supported in the stratosphere. The advantage of doing this is we don't need to have transit corridors on the ground like we normally have for high-speed rail, so no tunneling, no viaducts, and no land or permitting issues to create tracks on the ground. Similarly, it's advantageous compared to airplanes because you don't need to have airports. You simply need to have an elevator cable that takes you from the surface. The vehicles that travel in the system are very light. They don't have wings, landing gear, fuel tanks, or engines, and they travel very fast inside this evacuated tube, so they can go essentially 4 times the speed of sound because there's no air to slow them down. Another business model that's supported by the tethered ring is solar power generation. It makes a lot of sense to put solar panels up on a ring because they'd be above the clouds, they'd be above 90% of the atmosphere, 99% of the atmosphere. They have a clear view from horizon to horizon, so they get a longer day, or they're exposed to sunlight for longer. The panels will remain clean. They won't be damaged by hail, for example, so they don't need to be quite as expensive. And because the temperature at the altitude of the ring is minus 40 degrees C, this increases the panel's efficiency and its operational life, which saves you money. And whenever energy is generated renewably, you've got to deal with the intermittency issue. So tethered ring's mass stream contains 58 terawatt hours of kinetic energy. If you use just 0.5% of that energy for storing the electrical energy you generate with the solar panels, that storage is worth a lot of money. In fact, you can do this math and it works out to be worth $635 billion of storage, equivalent in lithium-ion batteries. Another business model is real estate and tourism. So the tethered ring can support habitats, and people can go up there and visit these habitats and look down upon the Earth. And this hopefully will create an overview effect where people start to see the planet from a different perspective, and maybe they'll make some lifestyle changes, or at least vote for leaders who will do more to prevent global warming. Now, we talked about trying to assess the cost of our mission to the moon and Mars by using space infrastructure. So for that, we made some assumptions. So we are assuming the wholesale electricity cost is just 5 cents per kilowatt hour, or 0.014 US dollars per megajoule. We'll assume that for every 100 tons we deliver to the moon or Mars, we need a 100-ton lander as well, so we need to launch that, which doubles the amount of mass we have to launch. We're going to assume an electrical to kinetic energy conversion efficiency of 50%, and we'll assume that the velocity the launcher's exit is 15 kilometers per second. So that's the speed that we leave the Earth, and that will get us to Mars faster than a typical journey with a Starship system, which means that the crew will have to bring along fewer provisions and will be exposed to less cosmic radiation on the way. This formula shows you the math. The launch costs are equal to the cost of electricity times mv squared over 2, which is the kinetic energy required to launch these vehicles, times the efficiency of the launcher. And when you do the math, it works out to 2.36 billion US dollars worth of energy to complete the mission. Now recall that the Starship mission was 607 trillion US dollars to complete the same mission. So as you can see, there's an enormous difference of 5 or 6 orders of magnitude here, which really justifies investigating whether or not it's possible to build such infrastructure at a reasonable cost. And we've created a model, an architectural model of the Tethered Ring, which you can see online, and you can use your browser's debug features to actually walk the code, set breakpoints, and adjust various parameters to, input your own assumptions if you like to see what it will cost. With the default set of assumptions, the estimated cost of a tethered ring is around $50 billion, which is very reasonable for our first reference design compared to the $607 trillion it will take to complete this mission to Mars. So I hope this is interesting and you'll take a look at the model and that you will consider spending some of your time looking more deeply into the topic of whether or not electromagnetic launch and active supported structures can be useful for our future ambitions with respect to colonizing the solar system, and also have very beneficial businesses that they support here on Earth as well. Thanks very much.